graph have unique weights, which means no two edges are the same weight, all edges are different weights, then there's only one minimum spanning tree of that graph. Okay, so in this example, the previous one we saw, if the graph does not have unique edge weights, which means at least one weight repeats like this, you can have more than one minimum spanning tree. This is one minimum spanning tree, and this is also another minimum spanning tree. They add up to 4. But if you don't have unique edge, like if you have unique edge weights, let's say this is a 3 and this is 1, 2, 4. Now you know if you run Kruskall's algorithm on this graph, you're going to pick up this, followed by this, followed by this. So this will be a minimum spanning tree. You cannot find any other minimum spanning tree on this graph if all the edge weights are unique. Okay? So what I mean, if all your edges are having unique weights, unique means distinct different weights, then you have only one minimum spanning tree for the entire graph. You cannot find more than one. So that's a theorem that we could prove again using the same idea of contradiction and everything that we met last time. Let's try to prove this. So the theorem is again, if the graph has unique edge weights, then you have only one minimum spanning tree. So how to prove this? Let's say you have a graph with unique edge weights, but let's say you have two different spanning trees. Both are minimum spanning trees for the same weight, of course. That you can have multiple minimum spanning trees, but they should add up to the same weight. So let's say you have two minimum spanning trees for a given graph with unique edge weights. Let's say the weight of this is equal to the weight of this. But they are different. Different means structurally different. They have some edge difference. So which means what? There should be one edge in one tree which is not in the other tree and vice versa, right? So it could be something like what we have there. We have one tree like this, another tree like this. So this could be a D and D prime, but they all should add up to the same weight. Okay? So which means there should be one edge which is like this E here, and it's not here, and it's here, and there should be one edge like E prime that is, let me use other convention. What convention we are using for the things? Let's see, one edge in T, okay, it's not a T prime. So this edge is here, that's not here, and this edge E prime is here, that is not here. Okay? So they should be structurally different, so there should be one edge that is here and not here, and one edge that is here and not here. Okay? So we want to argue that this is not possible if the graph has unique edge weights. Okay? So how is that possible? Alright. So we know from our previous discussion that what we can do. If we remove this E prime, it's not here. So if let's do it like this. If you put this E, which is here and not here in this graph, right, in this tree, you're going to create a cycle, right? If this E is included in this tree, it's going to create a cycle. And we know from our previous theorem that if you include an edge which is not fortunately there in a minimum spanning tree, you're going to create a cycle, and that edge is going to be the what? Maximum weight edge in that cycle, right? So in this small cycle over here, this edge E that we added is of the largest weight, right? So it's larger than all those edges, which means the weight of E has to be greater than the weight of E prime. And we know that it has to be strictly greater because all edges in this virtual graph are unique edge weights, right? So the weight of E has to be greater than the weight of E prime. If that is the case, coming back to this tree, we could remove E and have E prime on it, right? And that would even further lower the weight of T, because we know the weight of E is greater than the weight of E prime. This was the 5 and this is a 4, we have removed this and added this. So the weight of T would even be lower, right? The weight of the spanning tree would get lower, which means what? It's not a minimum spanning tree to start with. If you can further reduce the weight of a spanning tree, right? The previous one is not a minimum spanning tree, but our assumption is both are minimum spanning trees, right? So which means if weight of E is greater than the weight of E prime, T won't be a minimum spanning tree. But if it's the other way, if weight of E is less than the weight of E prime, what we can do? We could have E here and remove E prime from this T prime. So that would make the weight of T prime to go down, right? So, but we know again T prime is the minimum spanning tree to start with. So we cannot let the weight of T prime also to go down. So which means what we have established, weight of E cannot be less than E prime as well as the weight of E cannot be greater than the weight of E prime. So the only way these two edges can be related, the weights is what? Weight of E has to be equal to the weight of E prime. That's the only way they could be related. If the weight of E is less than the weight of E prime, we said we could retain E in E prime and remove E prime. Right? So that would lower the weight of this tree T prime and make it not a minimum spanning tree to start. If it's the other way, we could have E here as well. We could remove E like this and have E prime and that will lower the weight of T. But both are minimum spanning trees. But structurally different like this. So which means if you want both to be minimum spanning tree, this cannot be true as well as this cannot be true. So the only way the two edge weights can be related is the weight of E has to be equal to the weight of E prime. But what is our original assumption? The graph has unique edge weights. Okay? So if the graph has to have unique edge weights, right? That contradicts our assumption because we say if both of them have to be minimum spanning trees, the weights have to be equal. So that contradicts our original assumption that the graph has unique edge weights, which means what? No two edges have the same weight. Okay? So this way what we have proved, if a graph has unique edge weights, then you can have only one minimum spanning tree on the graph. You cannot have multiple minimum spanning trees. Okay? There's a last another property. If a graph has again unique edge weights, but this is in this case it's just in a cycle, the rest of the edges of the graph can be of the same weight if needed. So you have some graph and a cycle, and then you have some other edges also there. Okay. Now, the theorem states if a weighted graph has unique edge weights as part of the cycle, so this is the cycle, and all these edges that are part of the cycle are of unique weights. Unique weights means again different weights. Then what we need to prove is, the theorem is, the heaviest weight edge in the cycle will not be part of any minimum spanning tree on that graph. Heaviest weight edge means what? Let's say I give some values for these edges. The heaviest edge weight is this. So if you try to find a minimum spanning tree for this graph, that edge weight 7 will not be part of any minimum spanning tree. Okay, so that's the theorem. That's what it is. So if you have all the edges to be of some weight, like this, and you run your Kruskal algorithm on this graph, whatever the minimum spanning tree you get, you may get more than one minimum spanning tree, but none of them should have this edge. That's of the largest weight in a cycle. Okay? So how do we prove this? The only technique we are using is contradiction, right? So if you want to prove that this start with one vertex, go around, and then come back to the other vertex. Right? That's what is a cycle. Right? You have an edge from J to K, but you can also go around and come back to K. Right? So which means in this tree also you have the edge JK, and of course you cannot go and come back to K because it's a tree, but you can kind of form the two cuts involving these vertices J and K. Right? In this tree. And of course you cannot have them connected, because if you have them connected in the tree, it's a cycle. So, but you can split them into two cuts, right? And now, if all these edges are going to be what? Lower weight than this JK, you could have some edge that is part of this path connect the two cuts other than this edge JK, right? Because I have split the vertices into two sets, one that has J in it and one that has K in it, right? So which means the original cycle can be also split in some way where I have J in one cut and K in the other cut. So now the two cuts can be joined by some other edge that is on the path from J to K, like this. So that edge can connect these two cuts, and this edge need not be there. Right? Like in this case, if you assume this as some L and M, so you can connect this with this edge rather than this edge. And we know, based on what is given to us, the other edges have lower weights compared to this JK. So by adding that edge, in this case it is 3, edge weight 3, right? We are going to only reduce the weight of this tree, because we removed JK of weight, in this case 7, and we added an edge of weight 3. So by doing that, we are only reducing the weight of the tree further. So now again, we know that we started with a minimum spanning tree, so we could not reduce the weight further. Right? So which means if the heaviest weightage in a cycle is part of a minimum spanning tree, we would always remove that and add another edge to connect the two cuts, forming of the two end vertices, and making it not a minimum spanning tree. Right? So which means what? The heaviest weight edge cannot be part of any cycle. So a heaviest weight in a cycle cannot be part of a minimum spanning tree. If it was part of a minimum spanning tree, then we could do all these things. We could remove it and add another vertex. So that will lower the weight of the spanning tree, right? So that's the theorem. If you have the heaviest weightage in a cycle, it cannot be part of any spanning tree, minimum spanning tree. Okay? So these are the theorems in this. You don't need to know how to prove them. The other is getting worse. Change of weather. So last time we saw the maximum spanning tree also. How do we find the maximum spanning tree? Instead of picking the minimum edge weights, pick the largest edge weight. So you have 15, the largest one. So you see that there are two components. Then you can merge them. And then pick the next largest one, which is 11, and put it here. And it brings two different components, right? So that's how we find the maximum spanning tree. Okay. So the last algorithm in this module is this all paths shortest path. So what does it mean, all paths shortest path? With the Dijkstra's algorithm that we saw before, we started with one vertex and we found the shortest path from that vertex to all the other vertices. Now what we want to find here is the shortest path between any two vertices. Between any two vertices, what is the shortest path? Again, shortest path means a minimum weight path. The sum of all the edge weights should be minimum. Okay? We could use Dijkstra's algorithm for this. If you have, what is the complexity of Dijkstra's algorithm? Anybody remembers? I think it was V square log V. run it from one vertex, it is set of v square log v. If you repeat it at every other vertex, also it is v times this, which is going to be v cube log v. Right? Is that clear? So we'll see another algorithm, which is this Floyd's algorithm. That's going to be of complexity only v cube. So it's better than running Dijkstra's algorithm multiple times. So that's the advantage with this. And also in the Dijkstra's algorithm, I would have mentioned that one other assumption is all edge weights are positive. So you can't have negative edge weights there. But with this algorithm, you can have negative edge weights also. Okay? So that's another advantage of this. And you will get all the shortest path in one go. You don't need to do it multiple times. As you do the algorithm, you'll see that you can find the shortest path in one single or at a time. So before I further, so the fifth quiz, quiz 5, supposed to be next week, right? I'll make it take home, so I'm working on it, so I'll post it this afternoon. Okay, so keep checking the website. So it will have 5 problems, the minimum and maximum spanning tree, and then Dijkstra's algorithm, and then this one, and then the topological sort. Okay. So quiz 6 will be on the next module, which is distributed systems. That cannot be take home because it's not possible to come up with different things for different people. Be prepared for take quiz 6 in class. And final, I'll think about how to do that. The plan I have is I may give it 2 parts. The one part is the take home, you do and make it, and then some theorems. You have not proved theorems yet. So all the theorems that you have seen, I'll give you a list of things to read, and then you can come here and write the proofs. That's the plan I have. Okay, we'll think more about it, but tentatively that's what it is. Okay, so again the quiz 5, do it and bring it. And I see some people don't work out the entire thing, they just do probably a scratch sheet and write the answer. You have to show all your work on the sheet that you're submitting to me, like the matrix multiplication in the exam. You do all the multiplication in the scratch sheet and then just write the answer in your sheet. That's not the way to do it. Okay? So from next time, you should show all the work in the exam itself. See what I mean? Okay. Alright, so so we are going to again proceed in iterations, and here we require the vertices to be labeled from index 1 to n. So in general, the vertices, we have n vertices, so v1, v2 all the way to vn. So we label the vertices starting from index 1. So we'll have n iterations, and what we are going to do is in iteration 1, we are going to see if any 2 vertices vi and vj can be connected on a path that has only v1 on it. If possible, v1 as an intermediate vertex. v1 may not be possible to connect them through v1. It may be possible, may not be possible. You are going to check. In the second iteration, we are going to check if we can connect vi and vj through one or more vertices from the set v1 to v2, v1 and v2, which means v1 could be an intermediate vertex or v2 could be an intermediate vertex, depends on the paths that are available. So it could be possible that both v1 and v2 may be intermediate vertices. It could be just one of them is the intermediate vertex, or it could be that you cannot find any path that has v1 and v2 as intermediate vertex, depending on the graph. Okay? And the third iteration, we are going to see if we can connect again vi and vj through one or more of vertices from this set v1, v2, v3. Again, the objective is to find the shortest path, the minimum weight path from Vi to Vj. So we're going to start with this and then see, and let's say there's a path of some weight. Then by including one or more vertices from these cells, we are going to see if we can reduce that weight further. So we start with an estimate for each of this path, and then we are going to see if we can even further reduce the weights. See what I mean? So now let's do this general step. So we have Vi to Vj. You had some path from Vi to Vj in the k minus 1th iteration. K minus 1 means you have iterations 1, 2, 2 like k minus 1, k and so on, up to n iterations. The k minus 1th iteration, this is the path from Vi to Vj of some weight. That's what is indicated as Vk minus 1 with all the prefixes like this. So what it basically indicates is the weight of the path from I to j in the k minus 1th iteration. So let's say that it be some 17 or something. Now, you see here in each iteration what we are doing. We are adding one more vertex to be considered as a possible intermediate vertex. In the second iteration, we are adding vertex 2 as a possible vertex, intermediate vertex. In the third iteration, vertex 3. The other two vertices are already considered before. Right? So in the fourth iteration, we'll see if we can go through V4 and reduce the weight further. So in the kth iteration, what you're going to see is if we can go through Vk, basically from Vi to Vk, and then from Vk to Vj, and see if we can reduce the weight less than 17. Okay? So if we can go from Vi to Vk, and then from Vk to Vj, if we can reduce the weight, who's that? So if we can reduce the weight from Vi to Vj by going through Vk, okay? So Vi to Vk, now again, how do we know the weight of the path from Vi to Vk? Based on the k minus 1th iteration, there will be some estimate of the path from Vi to Vk. Similarly, there will be some estimate of the path from Vk to Vj, based on the k minus 1th iteration. And what does it mean? Again, k minus 1th iteration means all these intermediate vertices can be only V2, V1 up to Vk minus 1. They cannot be more than Vk minus 1 because that's what we are doing, right? In each iteration, the intermediate vertices can be only up to that iteration number. So in the k minus 1th iteration, all the possible intermediate vertices can be only up to V1, V2 up to Vk minus 1, a subset of them. So if this weight is some say 5 and this is say some 7, previously we have from Vi to Vj the path is of weight 17. Now by going through Vk, we can reduce it if possible. Then we'll go through Vk. 5 plus 7 is 12. So, I'm getting cold. So the path has to be then diverted through Vk. Right? So there was a path before from Vi to Vj, and from the Daxter's algorithm we know this term predecessor. Predecessor means if I want to reach from Vi to Vj, what is this vertex through which you can reach Vj, right? In this path from Vi to Vj, there would have been some predecessor, but what we have to do now, if we go through Vk, the predecessor, we are indicating that by pi. Pi of Vj has to be what? Whatever is the predecessor for Vj on this path from Vk to Vj. So instead of this vertex on the path from Vk to Vj would be the new predecessor. If we go through Vk, we have to reset the predecessor. Instead of this one, it has to be this one. So the predecessor has to be set like this. Whatever was the predecessor from Vk to Vj would be now the new predecessor from, you can also indicate like this, Vi to Vj. So the predecessor on the path from Vi to Vj is the predecessor on the path from Vk to Vj. set. For example, if this was say a 15 and this is say a 7, then 15 plus 7 is going to be more than 17. So if we cannot reduce the weight of a path, we'll stay with what we have. So then the predecessor will also remain the same. Okay? Is that clear? So we are going to proceed this in iterations. And so I have two examples. Let me tell you what kind of how the question will be in the exam. I'll give you a graph. I may not even give you a graph actually. I'll give you what is called the distance matrix. The distance or the weight matrix, either way you can call it, basically indicates the edges between any two vertices and their weights. So let's look at this. If I give you this matrix, what it means is from V1 to V1 or V2 to V2, from a vertex to itself, there's no edge because all the edge weights are 0. Right? So there's no edge from a vertex to itself. Then if it's infinity, it means there's no edge from that vertex to the other vertex. So from V1 to V4, there's no edge. Okay? And so you can see this, it's a directed graph. So there's an edge from V4 to V1, but there's no edge from V1 to V4. So V4 to V1, there's an edge of weight 2. So the graph is dense graph like this. Instead of representing all the edge weights here, we are representing that in the matrix. And we need to use a matrix to do all the iterations. So we could indicate all the weights in the matrix itself to start with. So like that, V2 to V1, there's no edge from V2 to V1, but there's an edge from V1 to V2. You have an edge from V1 to V2 of weight 3. Okay? But V2 to V1, there's no edge, so we have infinity. Okay? And then again V2 to V3, there's an edge from V3 to V2, but not the other way. So the edge from V2 to V3 is of weight infinity. When you say the weight is infinity, it means there's no edge. Okay? So what we want to find is shortest path between any two vertices. So even though there's no edge from V1 to V4, you can see in this graph you can move from V1, you can go to V3, then V3 to V2, and then probably from V2 to V2. So those are the paths we are going to find. If there's more than one path, we are going to find the shortest path, the minimum weight path. Okay? So the given graph could have like the weights like this, where if there's infinity, it means there's no edge between the two vertices. Again, all the edges